Hello, wonderful people. Here we are. It's chapter 34. We're going to pick up with section 6 and then go through the end of the chapter. This was the last slide from yesterday. Thought that'd be a nice place to start us off. Ohm's law. The little cartoons over there say voltage supplies the push. That is true. Voltage is what's pushing the electrons through the circuit. Resistance opposes the push. That's true. Even a copper wire has a little bit of resistance to current flowing. And if you're trying to push it through a motor or a computer, well, that's where all the energy goes, into the computer. And when voltage pushes and there's a little resistance or a lot of resistance, current results. Current flows. The electrons move. Okay. Now, let's talk about electric shock. So your body has a resistance. If you try really hard, you can get your resistance all the way down to about 100 ohms. That means you have to be soaked in water, preferably salt water, standing in the metal bucket and wet head to toe. Or you can get your resistance up to 500,000 ohms if you try really hard. And if you wear a rubber suit or rubber gloves, you can get it up over millions of ohms. But most people don't walk around wearing rubber gloves. So the best you can hope for is 500,000 ohms if your skin is very dry and you've got some thick soled shoes on. So if you touch the electrodes of a battery and your resistance is about 100,000 ohms, you would not feel 12 volts. And you know this because those little rectangular batteries, those 9-volt batteries, you can touch the ends of those and you don't feel any tingle at all. If you touch them to your tongue, you do feel a tingle, maybe even more than a tingle. It hurts a little. But let's not go doing that. So 12 volts you won't feel, and if you had a 24-volt battery and you were touching it with your hands, you could maybe just barely feel a tingle. But if you're wet and you have moist skin, then 24 volts could be uncomfortable. We'll talk more about this in a second, but for now, I'm just going to go through this. What you're feeling is the current that goes through you. And that first number is not a tenth, not a hundredth, it's 1/1000th of an amp. You can feel 1/1000th of an amp. If you get up, another way to call a thousandth of an amp is a milliamp, right? You know the phrase, you know what a millimeter is? It's 1/1000th of a meter. So a milliamp is 1/1000th of an amp. And that's a whole lot easier for me to say. So 1 milliamp can be felt, 5 milliamps is painful, 10 milliamps, and the muscle will spasm. 15 milliamps, and you can't control the muscle anymore. So if you get 15 milliamps of current going through your hand, your muscles just contract. And that's where electricians get themselves into trouble, because if they touch a wire that has current in it and they weren't expecting it, and you get more than 15 milliamps going through it, your muscles close, and now you can't let go. Even though you're still awake and conscious, you can't let go from your hand to let go of the wire, and that can be very scary. And then 70 milliamps, if the current goes through your heart, that's where you start to risk death. If you get 70 milliamps going through your heart for about a second, then you could die from that. Lots of people all over America are killed every year by current from household electrics, 120 volts that comes out of the socket. That last paragraph, the soles of your shoes normally do provide a very large resistance, so that's what saves most people. But if you're standing barefoot in a wet bathtub, the resistance of your body is very small. And actually, most deaths by electricity in American houses happen in the bathroom. Now, when I was a kid in the 70s, and even a teenager in the 80s, that was just unfortunate. But somewhere in the 80s, they invented that ground fault interrupter, and those started to get placed into bathrooms in the 90s. And nowadays, um, most houses that are older than that they've put in the GFI, and all new houses for the last 30 years have GFI built in. And the GFI does a great job of saving lives because if you start to get a shock, the GFI senses the shock and stops the current from flowing long before the breaker box down in the basement would. We'll talk more about how that works later. So the point is right here, right now, is that 120 volts is enough to kill you if you're wet in a bathtub and there's water all over you. So don't do that. Handling a wet hair dryer can be like sticking your fingers into a live socket. Bzz. That is true. Now, there are ground wires. Everybody knows what the ground wire is, the third prong on a plug that you plug into the wall. A lot of things only have the two prongs, but more and more nowadays, more things have the third prong. The third prong, there's a picture of it. So the two flat prongs, right there and right there, that's what is the path for current. You have the electricity coming in, and then it goes to the hair dryer or whatever, and then it comes back out because the electrons have to have a path for current to flow. So that's the path for current to flow. Now, if this just goes to ground, so if there's something broken in the appliance, the electricity goes to the ground and out this part of the plug. The idea being that it's going through that third prong and not through you. So that's another way that engineers have figured out ways to keep us safe from the electrical appliances in our homes. Quick question. If the resistance of your body is 100,000 ohms, what would the current in your body be when you are touched a 12-volt battery? Current equals voltage divided by resistance. So 12 divided by 100,000, when you plug that into your calculator, is 1/10,000th of an amp. So that's 0.1 milliamps. And that's small enough to be harmless. But if your skin is very moist and your resistance is down to 1,000 ohms, which is not hard to do, and then you touch the terminal of a 24-volt battery, they're around, how much current would you draw? 24 volts divided by 1,000 amps, that is 24 milliamps. And that's dangerous. That will definitely be painful. You might get spasms. If it goes through your heart, it probably won't kill you, but no guarantees. Direct current, DC. All that means is that the electrons are flowing in one direction. So they keep going one way through the circuit. The electrons come out of the battery into the object, and then out of the object through the second wire and back to the other side of the battery. Alternating current is electric current that goes back and forth. So down here, the current is going from left to right and then right to left to right, right to left, if you're looking at the circuit. The reason this happens is because at the generating station, you have a big bar magnet that's spinning, and while it's spinning around, it's making a voltage on one side of it and then the other. I don't want to get into those details though, so this is all you need to know. So here is what you need to know about alternating current. It is electric current that repeatedly reverses direction. And that's good enough. That's all you need. Now, let me be clear. Is there any difference between DC and AC as far as getting shocked? No. None whatsoever. Is there a difference as far as an engineer would care about? Yes. Are we going to go into that level of detail? No. Whoops, what did I do? I hit a button. Why can't I go forward? There we go. Sorry. Voltage in North America, and actually voltage all over the world, is all AC. And the voltage, the number for voltage in North America is 120 volts. Uh, when my parents were kids, it was uh, less than that, down to 110 volts maybe. And prior to 1900, it was only 110 volts. So over the history of America, we started at 110, then we moved up to 120. Now, because Europe didn't adopt electricity until a few years after America did, they work at 220 volts because, as the sentence up there says, by the time electricity became popular in Europe, light bulbs were available that would not burn out so fast at higher voltages. So Europe adopted 220 volts as their standard. The good news for Europe is it saves you a little bit of money. It's cheaper to operate 220 volts in a house and all over the place. The bad news is it's a little bit more likely to kill you. It's not twice as likely, despite what the math might suggest, but it's a little bit more likely. Um, so if you ever travel to Europe, you will notice that difference right off the bat because that's a big pain in the butt to deal with. Now, in America, we can get 240 volts in our home. It is possible. If you want to read the line down there below, that explains how, but I'm not worried about it. 60 hertz. Oh, that's also more about how you get 240 volts at your house. Oh, and then down at the bottom, electric stoves, some air conditioners, and some clothes dryers all do work on 240 volts. And they have very different looking plugs for them. So if you buy a house someday and have to, or even an apartment, and you have to worry about your clothes dryer and your stove, they have weird plugs. AC/DC was a great band.